All right, today we are talking about circuits and paths, which are walks or routes that you can take through a graph. Paths and circuits like these come up when working with this classical question known as the Bridges of Königsberg question. Back in the 1700s, the city of Königsberg had a total of 7 bridges going across the various rivers. So the question was, is it possible to, on let's say your evening stroll, to go for a walk that crosses every bridge exactly once? So let's try to do one. Let's say we start here and we work our way across, we come back, and then, oh hey, all of a sudden, now that we've crossed these 6 bridges, there's no way to cross the 7th without crossing one that we've already crossed. So this would be a path that doesn't work. The question is, well, maybe we just didn't try the right one. Is there a path, or is there a route through the city crossing these bridges that crosses every bridge exactly once? So that's the classical Bridges of Königsberg question. And a mathematician at the time named Euler came along and said, I think that the question that we're asking has more information to it than we need. We don't really care about the shape of these land masses. We don't care about the fact that, hey, this island maybe is somewhat rectangular or that type of information. We can abstract a lot of these ideas away and do what we did with our maps, which is transform this picture, this map, into a graph. So we are going to, as with the maps, give each landmass a vertex, and between vertices draw edges that correspond to the bridges. So we are going to connect two vertices if they have a bridge between them. And notice that our graph is not simple because we have edges, we have multiple edges going between a given pair of points. So for all of the questions involving things like paths and circuits, we're certainly not assuming that all of our graphs have to be simple. So by drawing this graph, we can, instead of asking the question about possible routes through the city, where it matters maybe what street we're taking, and instead ask the question about the graph itself, and say, all right, what is a route through the graph that meets whatever conditions we're after? All right, it wouldn't be a graph theory video without some definitions. These are just to make sure that we are using the same terminology to talk about whatever it is we're talking about. So a path is just a walk or a route through a graph, but we also want to specify that we're not doubling back exactly. We're never going to repeat an edge in a path. All right. A circuit is the same thing as a path with the extra condition that the starting vertex is the same as the ending vertex. We want to loop back around and end up back where we started. All right. Either paths and circuits can be what we'll call Eulerian, which happens if we utilize every edge. And because both paths and circuits specify that, hey, we don't want to use an edge more than once, there's an implied exactly once in this definition of Eulerian. We also say that a path or a circuit can be Hamilton if that path or circuit hits every vertex. So Eulerian is asking about the path's interaction with each of the edges. Hamilton is asking about the path's interaction with each of the vertices. So let's take a look at an example. Here is a graph with 5 vertices. We can specify a path through the graph by saying, hey, let's start here, and let's go from this left vertex to the right vertex, and then maybe up, and we can continue specifying what our route is through the graph. So because this route ended up at a vertex that was different than where it started, we say that this is not a circuit, however it is a path. Further, we can ask, is this path Eulerian and is it Hamilton? Well, it is Eulerian because we use each of the edges exactly once, but it's not Hamilton because we start at this vertex and then at some point we come back to that vertex. To be Hamilton, we need to use each vertex exactly once. So this is an example of a path that is Eulerian but not Hamilton. We can certainly specify a different route through this graph. So let's start at the same vertex, but instead start off by going down, and we can draw our arrows around the graph to specify a way of walking the graph. So this particular route is a circuit because we ended up back where we started. In a sense, with the circuit, it doesn't really matter what our starting and ending points are. We have a loop, we end up back where we start. All right. This circuit is not Eulerian because we're missing an edge. However, it is Hamilton because we hit each of the vertices. All right. So the two examples that I've gone through, one of which was Eulerian but not Hamilton, one was Hamilton but not Eulerian, it's certainly possible to be both or neither. So then a common question that we'll have about a graph itself is, does this graph support a particular type of path or circuit? Is it possible in a given graph to specify a route that meets some of these conditions? So the bridges of Königsberg question, which was phrased as, is it possible to go for a walk throughout the city such that we cross every bridge exactly once? Well, that's just saying, does this graph have a Eulerian path in it? Or depending on if we're specifying if we have to end up back at the same house where we started, maybe we want an Eulerian circuit. Either way, we're asking a question about the graph rather than asking a question about a particular path or circuit itself. So some property of this graph, some inherent way that this graph works, makes it so that it's not possible to find one of these Eulerian paths. This is one of the questions that you'll all be discussing in groups in class. Lastly, another related question that we can ask is known as the Chinese postman problem. It's called the Chinese postman problem because a Chinese mathematician, Quan Mei Kuo, was working on this in the 1960s, and it's commonly attributed to him. So the idea is that if we have a graph that does not have an Eulerian path on it, that there is no way of crossing every edge exactly once, well, what's the next best thing that we can do? What is the shortest route that we can take that hits every edge, but minimizes how much doubling up that we do? So let's look at our bridges of Königsberg graph. Let's say we start at the bottom and work our way up, then maybe work our way back. Still no problem here, we haven't duplicated any edges. But then now when we get to here, we still have an edge to traverse, but we can't get there. We have to maybe duplicate a certain edge. So we have to go back through this edge, and then we can finish our almost Eulerian path. So this graph does not support an Eulerian path, as Euler showed, but it isn't terribly far off. It's possible to, while only duplicating one edge, still traverse every edge. So while it's not possible to go for a walk through the city of Königsberg and cross every edge exactly once, it's possible to do so while only repeating a bridge once. So this is the question, like, what is the minimum amount of duplication can we do for a given graph? One way of answering questions like this is known as Eulerizing a graph. So if we decided that we needed to traverse a certain edge multiple times, maybe we will designate the idea that, hey, what if we change the graph by adding another edge? Is it possible to, in this new graph, find an Eulerian path? And if so, how do we generalize this procedure? How can we maybe add in some edges to transform a graph from one that doesn't support an Eulerian path to one that does? All right, so a relatively short video. Like many of these graph theory topics, I think it's really best to jump in and work on these questions in a hands-on way, rather than just being told that, hey, this is how something works. In light of that, I think our time is best spent working on these questions in class, rather than having too long of a video.